last few lectures, we have studied the kinetics of a particle. We have first discussed the Newton's second law of motion, how it can be used for solving the numerical problems of kinetics. Now, then we discussed the D'Alembert's principle also, which is essentially the same as Newton's second law. However, in the last lecture, we discussed another approach, that is work energy theorem, and also we did discuss the conservation of energy principle. Using that, we can solve the kinetics problem. Now, in this lecture, we will be discussing about the another approach of solving the problems of kinetics of a particle, that is impulse and momentum method. You know that mass and velocity of a particle are two things which influence motion and forces. Suppose you hit a wall with 100-gram steel ball and another man hits with 1 kg steel ball. Which one will provide more force to the wall? Which will do greater damage? You know that it depends on the mass. Mass, no doubt, has some influence, but it also depends on the velocity. If 100-gram ball and 1 kg ball both are moving at the same velocity, then naturally the 1 kg ball will do more damage. However, if the 100-gram ball is moving with a tremendously high velocity and 1 kg ball is moving slowly, then 100-gram ball will do more damage to the wall. Therefore, the mass and velocity are two important things influencing the force which can be applied by the moving body. We coined a function f is equal to, that is function of mass and velocity, that is half mv square, that is called kinetic energy. In this function, mass is having a power 1 but velocity is having a power 2. Why can't we think of many other type of functions? One simple function is that if we say that function is mass times velocity, can we get some quantity? Instead of telling that mass into velocity square, we can have mass into velocity, which is simpler. One can have, of course, that mass into velocity cube, but we are not familiar with such type of physical quantity which is popular. Now, if we just take mass into velocity, that means we define a function of mass and velocity, which in which that function g is mv, the product of the mass and velocity is called linear momentum of the particle. Linear momentum g is equal to mv. Now, linear momentum is a vector having the same direction as the velocity. Kinetic energy is a scalar, however, linear momentum is a vector. It has the same direction as the velocity. It is proportional to mass and velocity. Now, if you differentiate the linear momentum with time, you get mass into dv by dt. If the mass is constant, this becomes equal to mass times acceleration, which is equal to sigma f by Newton's second law. Thus, the rate of change of linear momentum is equal to the resultant force acting on the particle. Therefore, Newton's second law can be expressed in this form also, that is, the rate of change of linear momentum is equal to the resultant force acting on the particle. Note that the direction of g and dj by dt is not the same. If you differentiate a vector, you do not get a vector, or you do not always get a vector in the same direction. So v and dv by dt are may have different directions. Therefore, in this case, g and dg by dt are having different directions. In the component forms, we can write sigma fx is equal to g dot x, sigma fy is equal to g dot y, sigma fz is equal to g dot z, where dot indicates differentiation with respect to time. You can also write f is equal to dg by dt even when the mass is changing, and you can have then in this case dmv by dt. If you have a situation in which mass is changing, like in fluid mechanics problem in a control volume, then you may have, but velocity if it remains same, then you can have dm by dt into v, which is m dot v. So this is the thing, but in this course mainly we will be discussing rigid body behavior. Now we define other term, that is impulse. You know, when we apply a force on an object, it causes acceleration. If we remove the force, the acceleration vanishes. Therefore, it is important that how much time that force has been acting. So the force as well as time both provides the strength of some action. Therefore, the product of force and time is defined as linear impulse of the force. Suppose the resultant force sigma f, which may be a function of time t, acts from time t1 to time t2, then t1 to t2 integrated sigma f dt is the total impulse of that duration. So total impulse is the area under f and t curve. If you plot force on this axis in one dimensional case, and this is t, then this, if the force is acting like this between, then this area is sigma f dt, that is the total impulse of that duration. Now t1 to t2 sigma f dt can be written as t1 to t2 dg by dt by Newton's second law into dt, which gives you dg, that means g2 minus g1 r delta g. Hence, the total linear impulse on a particle of mass m equals the corresponding change in the momentum m, that is mv. By this, we can find out change in momentum without, that is r, in other words change in velocity, without really finding out acceleration. In the component form, these equations are like this: t1 to t2 sigma fx dt is equal to mvx2 minus mvx1. t1 to t2 sigma fy dt is equal to mvy2, where vy is the velocity component in y direction, minus mvy1. t1 to t2 sigma fz dt is equal to mvz2 minus mvz1, where vz is the velocity component in the z direction. If we plot the resultant force with respect to time, then T1 to T2 sigma f dt is the shaded area between T1 and T2. If we have the three components fx, fy, z, then we can plot fx component with time, fy component with time, fz component with time, and we can find out the area, that is sigma fx dx dt is equal to this thing. Like that we can calculate the final momentum. Thus the total impulse between time t1 and t2 is the area below the resultant force curve from t1 to t2. Total impulse is vector quantity. Now we have got a very important principle, that is called conservation of linear momentum. Since the time rate of change of linear momentum is equal to the resultant force acting on the particle, if there is no resultant force, the linear momentum is constant. This is the principle of conservation of momentum, which is valid for the system of particles as well. If two particles are colliding, one particle is exerting a force on the other particle. Similarly, the other particle is also exerting the force on this particle, but there is no resultant force on the system of particles. Therefore, the linear momentum will remain conserved. These particles may have different velocities. However, if this particle's mass is m1, this particle's mass is m2, this velocity is v1 and this is v2, so m1 v1 plus m2 v2 will remain constant because no force has been applied from outside. This is called conservation of linear momentum. So suppose there are two particles A and B that interact during an interval of time. If the interactive forces F and minus F between them are only unbalanced forces acting on the particle during the interval, it follows that the linear impulse on particle A is the negative of linear impulse on particle B. Here I am using the word interaction. The particles need not physically collide. They may apply only the forces and affect the motion, like the gravitational field or charged particle applying the forces on each other. So it is not necessary that there should be impact of the particles. Change in linear momentum delta g of the particle A is the negative of the change delta gb in linear momentum of particle B. That is delta Ga is equal to minus delta Gb, or Ga plus Gb is equal to constant, or delta Ga plus Gb is equal to 0. We have been using this principle. For example, suppose a bullet of mass m strikes a block of mass m resting on a horizontal smooth floor and gets embedded into it. If the velocity of bullet is v, find out the velocity of the block plus bullet after the bullet has embedded into it. Now applying the principle of momentum, since there is no external forces acting, so that mv is equal to m plus m vf, where vf is the final velocity. Thus, vf is equal to mv divided by m plus m. Now, this is the final velocity of the block. So if the block is resting on a smooth floor and a bullet of mass m moving with velocity capital V has embedded in it, then the final velocity of the block will be m capital V divided by m plus m. If the block is kept on a rough floor instead of the smooth floor, then what happens? In that case, if the bullet is striking, there is a frictional force also acting, but the magnitude of that force, if we assume that the impact duration is very small, then the force coming due to impact of the bullet is so high that the friction can be neglected. So therefore, in the beginning, Vf may still be considered as mv divided by m plus m. However, after that, its velocity will keep on reducing because of the friction. Now, let us calculate the kinetic energy of the system before and after the impact. Before impact, kinetic energy is equal to half mv square. After impact, kinetic energy has become half m plus m Vf square. Hence, the change in kinetic energy is equal to half m square divided by m plus m V square minus half mv square, because the final velocity is mv m plus m. Therefore, we have to say kinetic energy before, in the beginning, the kinetic energy was only half mv square. After the impact, block is moving with velocity mv square. So therefore, half m plus m mv square v square divided by m plus m whole square. So this gives you half m square m plus m v square minus half mv square. One can take half mv square common, which gives you m divided by m plus m minus 1, that is equal to minus half mm divided by m plus m v square. Thus, there is a loss of kinetic energy. This is because the force field is not conservative in this case, because the velocity, and this loss of this one has occurred, minus half m divided by m plus m divided by v square. Now, if we define another term, just like we defined linear impulse and linear momentum, we define now angular impulse and angular momentum. The angular momentum m0 of a particle about O is defined as the moment of the linear momentum vector mv about O. Thus, H0 will be R cross mv. This is a particle, it is having a linear momentum mv. Direction of the linear momentum is same as the direction of the velocity. Its position vector with respect to one fixed point O is given as R. Then we are defining the linear momentum about this point as R cross product mv. Now, the cross product of two vectors is also a vector. Therefore, the angular momentum is a vector. That is, angular momentum is also called moment of the linear momentum. Now, in the component form, this can be written like this: cross product of R cross MV gives us H0 is equal to M determinant Ijk xyz Vx Vy Vz, so that Hx is equal to M Vz Vy Vzy minus Vyz, Hy is equal to M Vxz minus Vzx, Hz is equal to M Vyx minus Vxy. These are the components of the angular momentum. If we take the moment of the forces about O, forces which act on the particle, then sigma m0 will be R cross sigma f, that is R cross mv dot, R cross mv dot, because sigma f is equal to mv dot. Now, since H0 is defined as R cross mv, we can take the time derivative of H0, and this is H dot 0 is equal to R dot cross mv plus R cross mv dot. R dot is nothing but v, velocity. So, v cross mv plus R cross mv dot. R cross mv dot is equal to, that this can be written as H0 is equal to R cross mv. Now, it has come v cross mv. Cross product of a vector with itself is 0. M is a scalar, it can anyway be taken outside. So, this term has become 0. Therefore, you have got R cross mv dot, which is nothing but sigma m0 as shown here. Therefore, H dot O is equal to sigma m0. Thus, the moment about the fixed point O of all forces acting on M equals the time rate of change of angular momentum of M about O. So, you find out the moment of the forces about the fixed point O, then it should be time rate of change of angular momentum about this one. So, this equation is very useful. Or you can write T1 to T2 sigma m0 dt is equal to H02 minus H01 or HO2 minus HO1, that is equal to delta HO. Thus, the total angular impulse on M about the fixed point O equals the corresponding change in angular momentum of M about O. This is called, this T1 to T2 sigma m0 dt is called angular impulse. Now, like we have the principle of conservation of linear momentum, we also have principle of conservation of angular momentum. We see the equation H dot 0 is equal to sigma m0. If sigma m0, that is the moment of the forces about O, is 0, then what happens? Then H dot O will become 0, and in that case this will be, so H dot 0 is 0, that means HO is constant. Thus, if the resultant moment about a fixed point O of all forces acting on a particle is 0 during an interval of time, then its angular momentum remains constant. Also, the total angular momentum for the system of the two particles remains constant during the interval. This means that this is valid also for the system of particles. We present one example based on the conservation of angular momentum. A particle of mass m tied at the end of an inextensible string is rotated at omega radian per second along a circle of r radius over a smooth horizontal tabletop. The string is pulled down through a slot at the center of the tabletop at a speed v. Calculate the speed of the particle when it reaches r by 2 from the center. Now the particle is acted by three forces: the force of gravity, the normal reaction of the table, which is equal to the force of gravity, and the tension of the string. The moment of the resultant force about the center is 0, that is r cross f is equal to 0. Then, hence, according to conservation of angular momentum, the angular momentum h remains constant, that is r cross mv is equal to h remains constant. R cross mv can be written as r cross m Vr Er plus V theta E theta, because the string is rotating, it has got Vr and also it is being pulled, so it has got two components, that is Vr and V theta. Thus, r cross m Vr Er plus V theta E theta, where Vr and V theta are the radial and tangential velocities of the particle respectively. Since direction of radial velocity and position vector coincide, this expression reduces to r cross mv theta E theta, that is h constant. Now, putting V theta is equal to r omega in this expression, we get r square omega is equal to h, that is constant, because V theta. So, V theta you put r omega, so this is omega square r, that is constant. Thus, for two different radii of the path of particle, r1 square omega 1 is equal to r2 square omega 2, which gives omega 2 is equal to r1 by r2 whole square omega 1. From the given problem, r1 is equal to r and r2 is equal to r by 2 and omega 1 is equal to omega. Therefore, the angular velocity of the particle at the radius is 4 omega. The resultant speed of the particle is under root v square plus 4 omega square r square, that is the velocity of the particle. So, this is the application of conservation of angular momentum. Now, I will be doing and discussing some problems based on the impulse and momentum and also the work and energy theorem. One problem can be of this type. Now, if there is a block acted by This is held by a spring. From here you fire a bullet through a gun. Now once it is fired, then say some velocity v and the mass of the bullet is m. This mass may be m. Then you have to find out that if you have to design a spring whose stiffness should not increase, whose displacement that so the question may be, design problem may be that design a suitable spring, which means find out spring constant so that maximum displacement deflection is limited to delta. In this case, you can apply the conservation of momentum principle to find out the horizontal velocity of mass m. Initially, the momentum remains conserved, therefore mass times Vx, where Vx is the horizontal component of the velocity, should give you mass times the velocity of the particle block V. Once we have find out the velocity, this velocity, this will be in the negative direction. That means when the bullet is going this way, it will go in this way. Now this block will now possess the potential energy, kinetic energy. That kinetic energy will be stored as potential energy in spring. That means half mv square is equal to half k delta square. Delta is given to you because that is limiting deflection, so you can find out the value of k. That is this thing. If the friction is also present, then you have to find out energy lost in friction. Then half mv square will not be equal to half k delta square. In that case, you can manage with little less stiffer spring. It will not, because some energy is also absorbed by the friction. So this is this type of problem. Another problems can be this type, that when the force profile is given to you, and that is force versus time like this, and you are required to find out the velocity of a particle which starts at rest from 0 and reaches this and what is its velocity after time t. In that case, you can apply the impulse momentum principle. Change in momentum will be equal to the total impulse, which is nothing but this area, and you can thus find out the final velocity of the particle without doing much effort. Now, if last lecture we did a problem that if the a truck, heavy truck and a light car both are moving with the same kinetic energy. Now if equal amount of braking force is applied, which one will stop by covering less distance? The answer was that both will cover the same distance without stopping. Now I put a question that if a truck and car are moving with the same linear momentum, and if the same amount of braking force is applied, which will stop first? In this case, both will stop first, because the change in momentum is same in both the cases. So Ft is equal to change in momentum. If the braking force is also same, then the time will be same. So this problem also has been done. You may have the problems of that kind where the mass is changing. Suppose you have a cart in which you are putting some sand through a hopper at some rate, that is C kilogram per second. If the mass of the cart is m, then in order to maintain the constant velocity, what force F needs to be applied? Neglect the friction. In this case, at certain time t, change in momentum is equal to m plus kt, because the mass after time t is m plus ct, this is c kg, multiplied by v, that is at certain time, then minus mv, that is in the beginning when nothing was there. Then the total change in momentum is equal to ktv, which is equal to force times ft, and thus we get F is equal to k times v. So we need to apply a force which will be equal to velocity, which is proportional to the velocity of the cart, and rate of, this is C, rate of filling the material. So F is equal to Cv, C kg per second is being filled. So this is what that you have done. It can be shown that momentum of a system of the particles will be equal to the momentum of the mass center of the particle. Momentum of the mass center of the particle is defined as the total mass into the velocity of mass center. We know if we have system of particles and let us say ith particle is of mass mi and its position is xi, then sigma mi xi is the total momentum of the system. Now we also have mass center x is equal to sigma mi, this is xi dot, xi is the position, so xi dot is by velocity, sigma mi xi divided by mass m. I can differentiate both sides with respect to time and I get a relation, that is x dot is equal to sigma mi xi dot divided by m. Thus m into Vc, where Vc is the x bar dot, that is the velocity of mass center, is equal to sigma mi xi dot. So velocity of the mass center of a system of particle is the that is momentum of the mass center of the particles is sigma mi x dot I. Thus we can use this equation for system of particles. Now let us to one interesting problem based on the angular momentum principle. You have got a pinion, that is a small gear connected with its pair, that is gear, and this is attached with the motor. So, this is motor gear and this is attached towards the load side. If this radius is R1, this is R2, then Q is equal to R2 by R1 is called gear ratio. These are two gears, so it is gear ratio, and which will be equal to omega 1 by omega 2, which is equal to alpha 1 by alpha 2. Linear velocity is same actually for both the gears. So, omega 1 into R1 is equal to omega 2 into R2. Now, if I indicate that torque by the motor is TA, that is basically IA times, where IA is the inertia of the armature plus this gear, IA times alpha 1 is the angular acceleration, plus if we make a free body diagram of this, you will see that it is having IA alpha plus it is having a resisting force F present here due to the other gear. That is how it transmits the torque, because it is rotating this gear. Suppose it rotates in clockwise direction, then opposing force has to come here like this. So, that thing is given by F into R1. That is the, you have to overcome that also. So, we have to apply that FR1. Now, similarly for the other gear, you have F is the force applied by the pinion. So, FR2 is equal to IL times alpha 2 plus TL, where TL is the load torque. Therefore, I can eliminate F from here and put in this. So, TA is equal to IA times alpha 1 plus IL times alpha 2 plus TL R1 by R2, which can be written as IA times alpha 1 plus IL alpha 2 plus TL divided by Q R1 by R2. That is, this R1 by R2 has been replaced by 1 by Q. So, this is not there. Now, you have to find out the gear ratio for minimum torque. So, for that you do dTA by dQ is equal to IA times, let us first represent TA in that form, because I may say that alpha 2 will be prescribed, that is, load has to accelerate with certain angular acceleration alpha 2, that means pick up of the load. So, therefore, better to put it IA LQ times alpha 2 plus IL alpha 2 plus TL divided by Q, or dTA by, now dTA by dq is equal to IA times alpha 2 minus IL alpha 2 plus TL divided by Q square. This is equal to 0 for minimizing the torque. So therefore Q is equal to under root IL alpha 2 plus TL divided by IA alpha 2. This is the optimum gear ratio. If TL is negligible, if TL is negligible, then Q is equal to under root IL divided by IA. This will give this. So therefore in this case the gear ratio is not dependent on alpha 2. It is the ratio between the moment of inertia of the armature, this one load inertia, moment of inertia of the load and moment of inertia of the armature. So this is what that answer has come. And now we have discussed about, now I am giving one example of finding out the friction torque of a disc experimentally. Suppose you take a disc, this disc is rotating on the bearings. In this case T is equal to I d omega by dt plus Tf, where Tf is the friction torque. Now if you rotate the disc and after that remove the torque, then the disc stops after some time. Therefore G, for that equation of motion is 0 plus I d omega by dt plus Tf, or d omega by dt is equal to minus If Tf by E, minus Tf by E of I. So that means if you plot omega versus time curve and you can take the slope of that, by that you can find out the friction torque. Friction torque Tf will be I times d omega dt. So this is the thing about that. Now we have, in this lecture we have discussed about the linear momentum equation and also angular momentum equation. What is the relation between the rate of change of linear momentum with the resultant force and the relation of rate of change of angular momentum with the applied moments. If we have taken, while calculating the angular momentum, we have taken the fixed point. If we have a relative frame of reference, then we can have like this: relative to x, y, z, some frame of reference, sigma, and if it is moving with a constant velocity, then sigma f dt will be m absolute acceleration times dt, and since it is moving with a constant velocity, therefore this will be m AL dt, which will be equal to m dVL or dm VL. Therefore, sigma f dt, that means this I can write as GL, that means linear momentum with reference to another reference frame xyz, which is moving with a constant velocity. So GL is equal to mv rel or sigma f dt is equal to dg rel or sigma f is equal to g dot rel. So the equation of the impulse momentum is valid. That means we can also write sigma f dt is equal to delta g rel in the relative frame of reference, which is moving with a constant velocity with respect to the system. In fact, we can also see that if we have the angular momentum about this thing, so this is h rel is equal to r rel plus g rel. Now if you take the time derivative, so h dot rel is equal to r dot rel plus g rel plus r rel plus g dot rel. Now r dot rel and g class rel are in the same direction, therefore this is 0, and this becomes r rel class sigma f, which is equal to sigma m. Therefore we have this equation as well, that sigma m is equal to h dot rel. Thus, relative to that reference frame which is moving with a constant velocity, we have all the equations. Not only this Newton's second law is valid, but we also have the valid that impulse momentum equations. We have already shown that even work kinetic energy theorem is valid, provided you find out the work in that relative frame of reference, and kinetic energy is the change in kinetic energy in that reference frame. Now if we pay attention to equation for angular impulse, angular momentum, here we have got the angular momentum. We see that we have derived it like this: h dot o is equal to r plus m v dot, and if we have a system moving with a constant velocity, then its in dot term its effect is not experienced. Means I can have, if it is valid for mv dot, it is also valid mv plus c dot, and therefore this is naturally, this relation holds good for point O which is moving with a constant velocity. but there R it is a fixed point, or this may not, if that point is having some velocity which is acceleration which is in the direction of the R, then also this holds good, because suppose you have a point O, H dot O is equal to R cross M, this is V of that particle, that means I indicate by VO plus VL, and we say that this is basically dot dot. If you can somehow make R cross V dot O equal to 0, then this equation can be written as H dot O is equal to R cross MVL. That means I can have the relative velocities only. So therefore, the third condition is that V dot O is in the same direction as R. That means point that particle is moving, accelerating towards R, away from the particle. In these situations, this can be used. Now, let us do a problem of this. Therefore, whenever you are provided a problem, you have to think that which principle will be more convenient to apply. For example, if the problem is that there is a spring and you put a mass m suddenly on it, what is the deflection of the spring? In this case, mass has been put suddenly. In this case, the application of conservation of energy seems quite appropriate. If we drop a mass m from a distance height h from the reference unstressed position of the spring, then the spring gets compressed by delta. mgh plus delta is the change in the potential energy. From the conservation of energy principle, this should be same as the potential energy stored in the spring during its maximum deflection. That time the kinetic energy is 0. So therefore, this gives us this relation. Now this gives a quadratic equation which can be solved to find out delta if the particle is dropped from a height h. But in case h is equal to 0, then this becomes mg delta. That means you just have put the particle suddenly on the spring, that is half k delta square, or delta is equal to 2 mg by k, 2 mg by k, and in that case the deflection will be 2 times the static deflection. Static deflection is mg by k. Similarly, if you have been provided a problem where particle of mass theta is particle at inclined plane, which is inclined at theta, this particle is sliding down, and this is friction force is also acting here. In this case, what will be the velocity when the particle has travelled distance s along the inclined surface? In this case also, the principle of work energy, that is conservation of energy, can be applied provided you take into account the frictional forces also. That is, we can say it is just work energy theorem mg sin theta minus mu mg cos theta are the forces and S is the distance covered, that is half mv square. Therefore, V is equal to under root 2g sin theta minus mu cos theta into S, which can be written as 2gh minus, well, h is this height, minus 2 mu cot theta. So, due to friction, the velocity will decrease. So, this is the, so we see that understanding of all the principles is important, that is Newton's second law and D'Alembert's principle, which are basically one, then impulse momentum and energy, work energy methods. These, whenever that appropriate, you should apply that appropriate this one in order to get the answer. However, it is true that by following any method, you should be able to get the answers. Only thing is that in some cases, a particular method may take more time.